Arc volcanoes often show evidence for new magma coming from the lower crust and interacting with old magma in the shallow crustal storage system. The nature of the upper crustal system will affect whether this new magma causes an eruption and what the eruption will look like. I have chosen this figure from a recent synthesis of Andean volcanism, whereby the rate of mafic recharge affects the nature of the resulting volcanism to illustrate this concept. What I'll discuss today is the idea that understanding interplay of old and new magma in the upper portions of the transcrustal system requires accurate time series information about what is being erupted. This can be obtained by frequent sampling throughout eruptions. I'll also show how time series data over longer periods can reveal where a volcano is in its life cycle and how this impacts its response to the introduction of new magma. Most real-time and near real-time volcano monitoring data, including seismic, geodetic, infrasound, remote sensing, and gas, are commonly plotted and analyzed as time series. This allows an understanding of how active volcanic systems evolve with time, how precursory signals escalate or de-escalate, and how eruptions progress and ultimately end. Despite this being a session on subduction zone volcanoes, I couldn't resist using the 2018 Kilauea eruption as a beautiful example of this, where geophysical signals tracked caldera collapse, dike opening, and sustained eruption. Of course, other recent subduction zone eruptions could be shown as well, such as Montserrat, Redoubt, Mount St. Helens, or Pinatubo. One of the reasons I chose to highlight Kilauea, however, is to show that geologic time series data can be as powerful as other data types for understanding ongoing eruptive processes. As described by Ganzeki et al. 2019, changing compositions of erupted lava from fissures showed tapping and then flushing of residual magmas within the lower East Rift Zone. Eventually, new summit-derived magma dominated the eruptive products, as shown in blue on the upper right. During this eruption, compositional data were available in near real time to inform the ongoing response. Additional later analyses validated the models that were developed from the initial data, and the overall effort demonstrated that geochemical analysis can inform hazard assessments during an eruption. As seen at Redoubt Volcano in Alaska in 2009, the earliest eruptive products often hold the key to eruption initiation. Following months of elevated seismicity, gas emissions, and melting of glacial ice, the 2009 eruption consisted of 19 explosions and lava dome growth. The upper panel on the left shows whole rock compositions of pyroclasts and lava throughout the eruption. The earliest sampled material contained low silica andesite, which was absent in later explosions and during the dome growth phase. Sampling the tephra from the early explosions required rapid mobilization to the field, as seen in the figure on the left. We interpreted that the low silica andesite ascended from the lower crust during the 8 or more months prior to the first eruption, but that the magma stalled and accumulated in the upper crust where its phenocryst rim and melt compositions were established. Ascent of new low silica andesite through stagnant, mushy, old intrusions, residual from earlier Redoubt activity, mobilized differentiated magma pockets and interstitial liquids. These are the high silica and intermediate silica andesites that fed the subsequently erupted lava domes. For the rest of the talk, I'd like to focus on Augustine Volcano, a frequently active volcano in Alaska's Cook Inlet that has erupted numerous times historically, last in 2006. The 2006 eruption started with a series of 13 explosive events that produced fall, pyroclastic flows, and lahars, as seen in blue and green on this map. This period was followed by 4 days of continuous block and ash flow production, known as the continuous phase, and shown in deposits, the deposits shown in pink on the map. And finally, an effusive phase that produced 2 lava flows down the north side of the edifice, as seen in brown. Like Redoubt in 2009, the eruption yielded mostly low through high silica andesites. Mapping of deposits from the eruption allowed sampling of many of the individual events. Petrologic study of products from Augustine, in contrast to readout, suggests that all of the erupted andesites had been stored in the shallow crust prior to the eruption. Recent experimental work by DeAngelis et al. In 2020 shows shallow storage for the high silica andesite consistent with geophysics and melt inclusion entrapment pressures. Note also that within a single end-member lithology, differences in some trace elements suggest multiple subtly different magma bodies. For example, as seen here with chromium concentrations in the low silica or LSA end-member. The presence of mafic phenocrysts, as well as basaltic inclusions, as shown circled in red on the right and first published by Steiner et al., indicate that the eruption was preceded by an injection of new basalt or basaltic andesite into the old, shallow andesitic magma system. Recent work at Augustine, led by Mary Benage, focuses on a specific interval within the 2006 eruption and looks at the transition between punctuated individual Vulcanian blasts of the explosive phase and what caused a transition to more sustained eruptive activity during the continuous phase. In this study, we focus on Event 9, a single Vulcanian blast on January 17, 2006, and Event 10, which occurred 10 days later and produced two pyroclastic density currents, a smaller one during early Event 10, and the largest PDC of the eruption, the Rocky Point pyroclastic flow, during later Event 10. Just after Event 10, or shortly thereafter, the continuous phase of the eruption started. Previous work had recognized an increase in the proportions of high and intermediate silica andesites at this transition point, and that is confirmed by componentry shown here on the left. Such pyroclast componentry is qualitative and based on visual characterization, but provides important information about changing role of different magmas throughout an eruption. In looking in detail at pyroclasts, we found that even within a single Vulcanian event, a range of temperatures, whole rock, and melt compositions were present. The two panels here show iron titanium oxide temperatures on the left and glass compositions on the right, symbolized by individual low silica andesite and high silica andesite pyroclasts from both events 9 and 10. We conclude that the heterogeneity observed shows that low to high silica andesites repeatedly ascended through shallow dikes, mixing and mingling prior to and during each Vulcanian explosion. Looking specifically at the transition to late Event 10, which produced the largest volume PF of the explosive phase and occurred just at the start of the continuous phase, we found a shift to more consistent ground mass glass compositions as shown on the right panel. As seen on the left, we also observed higher plagioclase number densities for the latter part of Event 10, suggestive of higher ascent rates. You can also see the later Event 10 plagioclase number densities are close to those observed for subplinian to plinian eruptions, whereas pyroclasts from Event 9 and early 10 are more similar to previously published values for Vulcanian explosions. We interpret this shift from heterogeneous ground mass glass compositions to more homogeneous products seen at that juncture of the eruption is due to an interconnection of ascent pathways within the shallow magmatic plumbing system, thereby tapping a larger magma body and shifting from punctuated, more closed system behavior towards open system behavior fed by this deeper magma body. The higher ascent rate accompanies this transition. This transition is visualized in this schematic cartoon on the left, where the 3 shows interconnection of larger bodies of low silica andesite and high silica andesite during late Event 10. Prior explosions were fed by smaller bodies or dikes within the shallow system. Overall, the eruption of heterogeneous andesites in 2006, fed by a spatially complex and heterogeneous system of small volume intermediate magma bodies in the shallow crust, is similar to what occurred in 1986 and 1976. This is shown very schematically on the right, where unrest is shown in gray and general eruptive activity is shown in red. Overall, these modestly sized dome-forming eruptions appear initiated by frequent injections of mafic magma from the deeper crust. Next, I'd like to look back further in Augustine's eruptive history to provide context in which to place the current magmatic system. In the middle photo, you can see a tephra section with several late Holocene tephras, first identified by Waite and Beget in their 2010 USGS professional paper, that spanned from a few hundred years to about 1700 years before present. To the left of that, a representative strat section that was logged high on the south flank of the volcano extends back even further to the early Holocene. Note that these tephras, while their volumes are not accurately known because of Augustine's island setting, are coarser and thicker than deposits from historical eruptions such as the ones I've just talked about. This can be illustrated by the yellow box that you see at the top of the photo that shows all of the post-1912 tephra falls fall within that short interval. When we look at whole rock compositions of tephras from early Holocene through 2006, we see gradual trends that reflect changes to the underlying magmatic system feeding these eruptions. Younger tephras are more enriched in incompatible elements such as potassium, as shown on this Harker diagram on the right, where samples are color-coded by time. We recognize that sampling bias has probably caused undersampling of older, more modest-sized eruptions, and this may especially impact the apparent lack of more mafic older tephras. The increase in incompatible elements, however, is present from the early Holocene through late Holocene but prehistoric tephras, and is evident even if you exclude the historical compositions, which are shown mostly in pink. In addition to the whole rock compositions from the previous slide, we've started looking at glass compositions as well, in part because that allows us to look at distal samples where a more complete and more easily dated tephra record is preserved. We have found similar trends in glass as whole rock, as seen on the left. Specifically, incompatible elements are increasing through time despite more mafic bulk compositions. Here we illustrate this with a ratio of strontium, which is compatible and largely constant with time, versus yttrium, which is incompatible and increases through time. Next, we've investigated what intrinsic controls could underlie this change. First, temperatures calculated with magnetite-ilmenite pairs. These seem to increase into the late Holocene, as shown on the upper right. With this change, we observe an obvious change in mineralogy as well, specifically amphibole, which was very abundant in early Holocene tephras and rather rare in late Holocene and historical eruptions. Water concentrations, however, are not appreciably lower, as we might expect if magmas are drier. This is shown on the lower right. We're still at the speculation stage about why this change is occurring, or these changes are occurring. Possibilities, which aren't all mutually exclusive, include increased mafic recharge, which would lead to hotter eruption temperatures, less amphibole, and less chance for large, cool, evolved bodies to assemble. Other possibilities include lower crustal or mantle source of the mafic input is changing, or perhaps more heat is required to mobilize eruptible magmas in the upper crust as these upper crustal magmas become more refractory. Understanding the cause and effects between these changes in the magmatic system and changes in the style and magnitude of volcanic eruptions will assist in forecasting future activity at Augustine and similar volcanoes. I'll conclude by restating that time-constrained samples of eruptive products are key to understanding the current state of a volcanic system, what initiates eruptions, and what causes changes in eruptive style. And also, I just want to show these photographs of samples from the 2018 Kilauea eruption. collected at HVO. JAWS, collecting samples from the Mount St. Helens lava dome in 2006, and Mount Lowen sampling ash samples from the 2018 eruption of Veniaminoff in Alaska. Thank you.